Before the first stars formed, motion was already present. Gas drifted, gravity gathered matter, and tiny sideways movements began to shape the cosmos. Today, galaxies rotate, planets spin, moons orbit, and even particles carry a strange kind of spin. The universe does not need a motor to keep moving. Its motion is written into the laws of nature. This is the story of why the universe cannot stop spinning. Like the video, subscribe to the channel, and drift into the quiet science of cosmic motion. At the wider scale that can be observed, the universe presents itself as a vast field of light and darkness, extending in all directions without visible edge. Galaxies gather into faint patterns, yet the overall view remains quiet and balanced. Observations show that, on this scale, matter spreads out evenly when averaged over very large distances. No preferred direction appears, and no large axis of rotation is confirmed. The universe expands, with distant galaxies moving away as space itself stretches. This expansion defines the broad motion of the cosmos, not a spinning around a central point. Careful measurements of the background radiation, the faint afterglow of the early universe, reveal tiny variations in temperature. These variations are extremely small, differing by only a few parts in 100,000. They map the early distribution of matter and energy. Their pattern shows no clear sign of a universal spin. If the entire universe were rotating as a whole, this background would display a consistent directional pattern, like a faint swirl across the sky. Observations indicate that such a pattern does not exist within current limits of detection. The concept of rotation begins with a simple idea: an object turns around an axis. For a planet, this axis passes through its center. For a galaxy, it may be a broad region around which stars orbit. At the scale of the observable universe, defining such an axis becomes difficult. There is no outer boundary to mark a frame of reference. Space itself is part of the system. Without an external viewpoint, rotation must be inferred from internal patterns, and those patterns remain remarkably uniform. Even so, motion is everywhere. Galaxies move relative to one another. Groups of galaxies drift, pulled by gravity toward denser regions. This motion, however, does not form a single coordinated spin. It resembles gentle flows rather than a unified turning. The expansion of space dominates these motions, carrying galaxies apart over billions of years. The farther a galaxy lies, the faster it appears to recede, a relation known from consistent observation. At this larger scale, the laws of physics describe a universe that is the same in every direction and at every location, when viewed broadly enough. This principle, often called uniformity, allows scientists to model the cosmos without assigning it a center or a preferred orientation. In such a framework, the idea of the universe spinning like a wheel loses meaning. Instead, rotation appears only within smaller structures that form inside this expanding background. The absence of a detected global spin does not imply stillness. Rather, it reflects a deeper kind of motion that does not align into a single direction. Energy, gravity, and the initial conditions of the early universe combine to create countless local rotations without producing one overarching turn. Observations indicate that the early universe began in a hot, dense state, expanding rapidly. Tiny irregularities in density seeded later structures. These irregularities do not show signs of an initial global twist. It remains uncertain whether an extremely small rotation could exist beyond current measurement limits, but any such motion would be far weaker than the rotations seen in galaxies and stars. The horizon of observation marks the limit beyond which light has not yet reached. This boundary grows over time as light travels through expanding space. Within this horizon, the universe appears consistent. Beyond it, information is not yet available. The concept of spin at that unreachable scale cannot be tested directly. Therefore, conclusions rely only on what can be measured within the observable region. Light from distant galaxies travels for billions of years before reaching detectors. During this journey, the expansion of space stretches its wavelength, shifting it toward longer, redder light. This effect reveals the rate of expansion and helps map the large-scale structure. Nowhere in this mapping does a dominant rotational signature appear. Instead, the pattern resembles a network of clusters and voids, shaped by gravity and expansion rather than by a central spin. At this outermost region, the universe behaves less like a rotating object and more like a growing framework. Motion exists as separation, drift, and gentle flows, not as a coordinated turn. Rotation, in the familiar sense, emerges only when matter gathers and interacts under gravity. At the scale of the cosmic horizon, matter remains too evenly distributed for such collective turning to dominate. Thus, the universe at its largest visible extent does not spin as a whole. Instead, it provides the stage upon which smaller systems form and begin to rotate. The question of why the universe cannot stop spinning finds no answer here, because at this scale, there is no confirmed spin to stop. What exists instead is a calm expansion, within which countless local rotations will later arise. Inside the broad horizon of observation, the universe begins to show its first visible pattern. Galaxies do not scatter like grains laid evenly on a table. They gather into long threads, wide sheets, and quiet knots, with immense empty regions opening between them. This arrangement is called the cosmic web, because the large structures resemble connected strands stretching through space. The comparison is only a guide for the mind. The web is not woven from solid lines. It is made of galaxies. Gas, dark matter, and gravity spread across distances so large that ordinary measures lose their familiar scale. The cosmic web forms from slight differences in density that exist in the early universe. Some regions contain a little more matter than others. Gravity acts more strongly in these places, drawing in nearby material. Over time, the denser regions become denser still, while less dense regions lose matter and grow into voids. This process is slow and steady. It does not require a central pull from one place. It happens everywhere at once. Wherever small differences allow gravity to gather matter into larger forms. At this scale, the idea of spinning becomes more subtle. The cosmic web itself does not rotate like a wheel. There is no single center, no rim, and no shared axis, yet the matter inside it is never entirely still. As gas and dark matter fall toward growing structures, their paths are uneven. A stream of material approaches from one side, another from a different direction, and their combined motions create gentle turning in smaller regions. This turning is not imposed by the whole universe. It arises naturally from imbalance. A key idea in this movement is angular momentum. Angular momentum is the tendency of moving matter to keep turning around a point or along a path. Once matter gains this kind of motion, it is hard to remove unless another force or interaction carries it away. In the cosmic web, angular momentum appears when gravity pulls matter along curved, uneven routes. A slight sideways motion becomes important as material falls inward. The inward fall tightens the motion, and a slow drift can become a larger turn within a forming structure. The strands of the cosmic web guide matter like broad valleys guide water. Gas and dark matter move along these filaments toward denser intersections. Galaxies often form inside the strands or near their crossings. Their later rotations are shaped partly by how matter arrives. If material flows in from one side more strongly than another, the growing system receives a preferred direction of motion. If several streams meet at angles, their motions combine into more complex turning. The result is not universal spin, but many local rotations born from large-scale flow. Dark matter plays a central role in this region. It does not emit light, and it does not form stars. Its presence is inferred from gravity, because visible matter moves as if much more mass surrounds it. In the cosmic web, dark matter creates the main gravitational framework. Ordinary gas falls into this framework and later cools, gathers, and forms galaxies. The movement of dark matter is therefore part of the hidden structure behind visible spin. It shapes where matter gathers and how it approaches the places where galaxies will grow. Voids form the quieter regions between the strands. They are not completely empty, but they contain far fewer galaxies than the filaments and knots. Their expansion is less restrained by gravity because they hold less matter, as denser regions pull material away. Voids become larger and emptier over cosmic time. This outward thinning adds to the contrast of the web. Around the edges of voids, matter flows towards surrounding filaments, and these flows can add slight sideways motions to the structures they feed. The web is also shaped by expansion. Space stretches everywhere, carrying distant structures apart. Gravity works against this stretching in dense regions, slowing it and sometimes overcoming it locally. The balance between expansion and gravity gives the web its large pattern. Where matter is too thin, expansion dominates. Where matter is dense enough, gravity gathers and binds it. Rotation begins only where enough matter becomes connected by gravity, and where uneven motions avoid direct collapse. Because the web is so vast, its motion is usually studied through maps and models rather than through direct visible change. Redshift surveys measure how galaxy light is stretched, giving both distance and motion along the line of sight. Computer models begin with early density variations and allow gravity to work over billions of years. These models reproduce filaments, sheets, and voids with striking agreement, which supports the view that the web grows from gravity acting on small initial unevenness. The word spin can suggest a simple turning object, but in the cosmic web the motion is distributed and layered. Filaments may show preferred directions in the way galaxies align, yet these patterns are statistical and not absolute. Observations indicate that some galaxy spins and shapes have relationships with the filaments around them. These relationships help reveal how matter has flowed over time. It remains uncertain how all of these alignments develop in detail, because they depend on environment, mass, and the history of each system. Across this region, the universe appears calm from a distance. The filaments do not whirl visibly, and the voids do not churn like storms. Their changes unfold over billions of years. A galaxy crossing a filament does so slowly in human terms, though its speed is great by ordinary measures. Gravity does not rush in sudden gestures. It draws, redirects, and gathers. From those slow redirections, turning motions begin to appear. The cosmic web therefore gives the first clear setting for rotation without requiring the universe itself to spin. It shows how structure can create motion from small differences, and how motion can become organized when matter gathers. At the outer horizon, the universe expands without a confirmed global turn. In the web inside that horizon, the expansion remains, but gravity writes faint paths through it. matter follows those paths, and some of those paths bend. Where they bend and converge, the seeds of lasting rotation are formed. Where the strands of the cosmic web meet, gravity gathers matter into larger assemblies. These regions become galaxy clusters, the most massive bound structures in the universe. A cluster can contain hundreds or thousands of galaxies, along with hot gas and a wide halo of dark matter. It does not sit apart from the web. It grows from the web, drawing material along filaments and holding it in a shared gravitational field. From far away, a cluster may seem like a calm gathering of lights, but within it, motion continues in many directions. A galaxy cluster is not a single solid object. It is a community of separate bodies moving through a common region. Each galaxy follows its own path. Some travel near the center, while others pass through the outskirts. The hot gas between galaxies fills much of the space and shines in high-energy light because it has been heated to extreme temperatures. Dark matter surrounds and penetrates the whole structure, providing most of the mass that holds the cluster together. The visible galaxies mark only part of the cluster's true shape. At this scale, rotation appears less like the steady turning of a disk and more like the memory of many arrivals. Clusters form by repeated mergers as smaller groups fall together over billions of years. One group may approach from one filament, another from a different filament, and a stream of galaxies may enter at an angle. These entries rarely point directly toward the exact center. Their paths have sideways components. When they become bound within the growing cluster, those sideways motions contribute to the cluster's angular momentum. The spin of a cluster is difficult to describe because the structure is broad and irregular. A planet has a surface and a clear turning axis. A galaxy cluster has no surface in the ordinary sense. Its edges fade into the surrounding web, and its members are spread across millions of light years. Scientists therefore measure rotation statistically. By studying the motions of galaxies and gas within the cluster, if one side tends to move toward observation while the other moves away, a broad rotational pattern may be present. Such patterns are usually modest compared with the random motion of individual galaxies. The inner pull of a cluster is strong, but the motions inside it are not orderly at first. A newly formed or merging cluster is disturbed. Galaxies rush through, gas is compressed, and shocks move across the hot medium. These shocks are not sound in the familiar air-filled sense. They are pressure waves traveling through thin, hot plasma, a gas whose particles have been separated into charged pieces. As groups collide, their gas slows and heats. While galaxies and dark matter pass more freely through one another, the result is a layered motion, with different parts responding in different ways. This difference between gaseous galaxies and dark matter helps reveal the cluster's history. Gas feels pressure and can be stripped away. Galaxies are compact, so they mostly interact through gravity. Dark matter appears to pass through collisions with little direct resistance, leaving its presence marked by gravitational lensing, the bending of background light. In merging clusters, the separation of these components shows that a cluster is not one simple rotating mass. It is a place where several kinds of matter carry motion differently. Even when a cluster settles, it does not become still. Galaxies orbit within its gravitational field, though their paths are often elongated and tilted rather than circular. Some pass close to the center and then move outward again. Others remain in the outer regions for long periods. Encounters between galaxies can alter these paths, but direct collisions between stars are rare because stars are separated by enormous distances. The cluster's gravity does most of the shaping. slowly redistributing motion through repeated passages. The hot gas also carries traces of rotation and turbulence. Turbulence means irregular, mixed motion rather than smooth flow. In clusters, turbulence can arise from mergers, falling groups, and energy released near central black holes. It spreads through the thin plasma and affects how heat moves. Rotation in the gas may appear when a merger brings in material with a shared sideways motion. Over time, some of that organized motion fades into turbulence, while some remains as broad circulation around the cluster center. The growth of a cluster shows why spinning motion is so persistent in the universe. Gravity draws matter inward, but it cannot easily erase sideways motion. If falling material had no sideways motion at all, it could collapse more directly toward the center. In reality, perfect direct fall is unlikely. Small imbalances always exist. Matter approaches from uneven directions, and these uneven paths generate angular momentum. Once angular momentum is present, the system must redistribute it rather than simply lose it. Some of it remains in galaxy orbits, some in gas motion, and some in the rotation of smaller structures inside the cluster. Clusters also influence the galaxies they contain. A galaxy entering a cluster may lose gas as it moves through the hot medium. This process can reduce future star formation. Gravitational encounters can stretch galaxies, disturb their shapes, or pull material into long streams. These changes affect the internal motion of galaxies, but the cluster's own scale remains larger and less organized. It is a wide gravitational environment where spin is present as a collective tendency, not as a clean and simple turn. In a mature cluster, the central region often contains a large galaxy that has grown through many mergers. Around it, smaller galaxies move through a deep gravitational well. The cluster does not need a rigid body to preserve motion. Its rotation, when present, is held in the paths of its members and in the flow of its gas. The motion is distributed across space, carried by separate parts that remain bound together by gravity. Thus, the galaxy cluster becomes a deeper region in the path from the outer universe inward. It is smaller than the cosmic web, but still immense, shaped by the same principles of gravity, imbalance, and inherited motion. It shows that rotation does not require a perfect wheel. It can arise in a gathering, in a merger, in the angled arrival of matter from long cosmic strands. The cluster turns only faintly and unevenly, yet it preserves the same rule that appears again and again across the universe. Motion that begins with a slight sideways path does not simply disappear, it is carried inward, rearranged, shared, and held. Within the wider gathering of clusters and groups, spiral galaxies show rotation in a clearer and more graceful form. A spiral galaxy is a broad system of stars, gas, dust, and dark matter, held together by gravity and arranged often in a flattened disk. Its bright arms curve around a central region, tracing places where gas, young stars, and dust are more visible. The galaxy does not spin as a solid object. Its parts orbit the center at different distances, moving through a shared gravitational field. The turning is steady enough to give the galaxy its shape, yet flexible enough to let stars and clouds follow their own paths. A spiral galaxy forms from matter that has fallen inward from a larger halo. A halo is a wide region of matter around the visible galaxy, especially dark matter, extending far beyond the bright disk. As gas collapses into the center of the halo, it carries angular momentum, because this motion cannot simply vanish. The falling gas settles into a rotating disk instead of dropping straight into the middle. The disk becomes the main stage where stars form, gas clouds collide, and spiral patterns appear, rotation is therefore not an added feature. It is part of how the galaxy becomes a galaxy. The disk is thin compared with its width. Stars and gas mostly move around the center in the same general direction, although their paths are not perfect circles. Gas clouds are more likely to collide and settle into a smooth rotating layer. Stars pass through one another without direct contact and keep more varied orbits. Dust mixed with the gas absorbs and scatters starlight, making dark lanes visible in many spiral arms. These lanes show where matter is dense enough to block some light, and where new stars may form. The center of a spiral galaxy often contains a bulge, a rounded concentration of older stars. Around it, the disk stretches outward into the arms. The arms are not fixed material bands like markings painted on a wheel. They are patterns of higher density moving through the disk. Stars and gas enter and leave these patterns as they orbit. Gas compressed in an arm can cool and form new stars, making the arm appear brighter. The visible spiral shape is therefore a pattern carried by rotating matter, not a rigid structure turning all at once. The rotation of spiral galaxies reveals one of the strongest clues for dark matter. If only the visible stars and gas supplied gravity, the outer parts of many galaxies would be expected to orbit more slowly than they do. In the solar system, planets farther from the Sun move more slowly because most of the mass lies near the center. Spiral galaxies behave differently. Their outer stars and gas often move at nearly the same speed as material closer in. This pattern is called a flat rotation curve, meaning that orbital speed remains roughly steady across much of the disk. The flat rotation curve indicates that additional mass surrounds the visible galaxy. This mass does not shine like stars, but its gravity affects motion. Dark matter provides the simplest widely supported explanation. It forms an extended halo, adding gravitational pull at large distances from the center. Because of this halo, outer stars can move faster than visible matter alone would allow without flying away. The galaxy keeps turning because gravity and motion remain balanced. Stars fall inward constantly under gravity, yet their sideways motion carries them around the center. This balance is orbital motion. A star in a spiral galaxy is not held up by a surface or fixed track. It is always falling toward the center of mass, but because it also moves sideways, it follows a curved path. The same principle holds for planets around stars, though the galactic case is more complex because mass is spread through the disk, bulge, and halo. Every star responds to the combined gravity of the whole system. The result is a slow, persistent circulation lasting hundreds of millions of years for a single orbit in many regions of a galaxy. The galaxy's rotation also shapes its gas. Gas clouds collide, compress, and exchange energy. Collisions allow gas to settle into a thinner disk than stars. When the gas becomes dense and cool enough, gravity pulls parts of it together into star-forming regions. These regions may shine with young, hot stars that light nearby gas. Over time, massive stars return material through winds and explosions, stirring the surrounding medium. The disk remains a place where rotation, gravity, cooling, and heating work together. Galactic rotation is not perfectly smooth. Bars may form across the central region of some spiral galaxies. A bar is a long structure of stars and gas crossing the middle, rotating as a pattern within the disk. It can guide gas inward and reshape stellar orbits. Spiral arms may strengthen, fade, or change as the galaxy interacts with nearby companions. A close encounter can stretch a disk, pull out tidal tails, or trigger new star formation. These changes disturb the motion, but they do not erase the basic angular momentum of the galaxy. Angular momentum is conserved when no outside torque removes it. A torque is a twisting influence that changes rotation. Galaxies can exchange angular momentum through mergers, bars, spiral patterns, and interactions with their halos. Even then, the motion is redistributed rather than simply destroyed. Some matter may move inward while other matter moves outward, carrying angular momentum with it. This exchange helps explain why disks evolve over time while continuing to turn. The direction and amount of a spiral galaxy's rotation come from its formation history. Matter falling into the early halo arrives from different directions, guided by the cosmic web and by nearby structures. The combined motion gives the forming galaxy a net spin. The spin is not perfect or predetermined. It is the result of many small pulls and flows adding together. Once the disk forms, its organized rotation becomes one of the most stable features of the galaxy. From far away, a spiral galaxy may look like a quiet wheel of light. In reality, its turning is made of countless individual orbits. Stars move through the disk, gas clouds drift, collide, and cool. Dust traces denser lanes. Dark matter shapes the outer motion without shining. The galaxy continues to rotate because its matter carries angular momentum, and because gravity binds that motion into curved paths. Nothing in the galaxy needs a motor to keep it going. In space, motion does not fade unless something acts to remove or redirect it. The spiral galaxy therefore gives a clearer answer to why so much of the universe keeps turning. Rotation survives because empty space provides little resistance, and gravity changes the direction of motion more than it removes motion. Matter does not stop merely because time passes. It keeps the movement it has inherited, while gravity folds that movement into orbits. In the broad disk of a spiral galaxy, the principle becomes visible as stars and gas circling quietly around a luminous center, held in a turning pattern that can last for billions of years. At the center of a spiral galaxy, the structure changes from a wide, thin disk to a dense and layered region, where motion becomes more concentrated. The galactic center gathers stars, gas, and dust into a smaller volume, and the gravitational pull grows stronger toward this inner region. The brightness often increases, not because stars shine more intensely on their own, but because many stars are packed closer together. Their combined light creates a glow that marks the core of the galaxy. Within this region, rotation continues, yet its character shifts as gravity deepens and orbits tighten. The central region may contain a bulge, a rounded collection of older stars that move in a variety of paths. These paths are not limited to a flat plane like the disk. Instead, they fill a three-dimensional space, forming a thick and extended structure. The motion of these stars includes rotation around the center, but also random components that give the bulge a more spheroidal shape. This mixture of motion reflects a long history of interactions, mergers, and gradual rearrangement under gravity. Near the very center, evidence indicates the presence of a supermassive black hole. This object contains a mass equal to millions or billions of suns, concentrated into a very small region. It does not shine by itself, but material falling toward it can heat and emit strong radiation before crossing the boundary from which no light escapes. The black hole's gravity dominates the motion of nearby stars and gas within a certain distance. Beyond that region, the combined mass of stars and dark matter becomes more important. Stars close to the central black hole move at high speeds along curved paths. Their orbits can be measured by observing their positions over many years. These measurements show that the stars follow predictable trajectories, which allows the mass of the unseen central object to be calculated. The motion is not chaotic without rule. It follows the same principles of gravity and angular momentum that apply throughout the universe. But the stronger gravity produces faster and tighter orbits. Gas near the center behaves differently from stars. Gas can collide, compress, and lose energy through radiation. As it loses energy, it can move inward more easily than stars, which do not collide directly. This inward movement forms rotating structures such as disks or rings close to the central black hole. These structures can feed material into the black hole over time. As gas spirals inward, it heats and may emit bright radiation, creating what is known as an active galactic nucleus in some galaxies. Rotation in the central region is therefore layered. The bulge shows mixed motion with partial rotation and random paths. The inner gas can form a more organized rotating disk. The stars nearest the black hole trace rapid orbits shaped by intense gravity. Each component carries angular momentum, and each redistributes it through different processes: collisions in gas, gravitational interactions among stars, and the influence of the central mass all contribute to how motion is shared and maintained. The presence of a bar structure in some galaxies adds another feature to the central region. A bar is an elongated concentration of stars and gas that extends across the inner disk. It rotates as a pattern and can channel gas inward. As gas flows along the bar, it may lose angular momentum and move closer to the center. This process can increase star formation near the core or supply material to the central black hole. The bar does not stop rotation. It changes how angular momentum is distributed, shifting motion from one region to another. The central region also contains dense star clusters. These clusters may form in place or be drawn inward over time through gravitational interactions. As they move through the central environment, they can lose energy and sink closer to the core, a process known as dynamical friction. This effect arises because a moving object in a field of many smaller bodies creates a wake of increased density behind it. The gravitational pull of this wake slows the object, causing it to move inward. In this way, motion is transferred rather than erased, and angular momentum is spread among many stars. Despite the strong gravity and frequent interactions, the central region does not come to rest. Motion persists because there is no simple way to remove it entirely. Gas can radiate energy and fall inward, but its angular momentum must be carried elsewhere, often outward through interactions with other gas or through magnetic effects. Stars exchange energy and momentum through repeated encounters, but their overall motion remains bound within the system. The black hole can absorb matter, yet it does not absorb angular momentum in a way that halts the rotation of the entire region. Instead, it becomes part of the ongoing balance. Observations indicate that central regions vary from one galaxy to another. Some are quiet, with little gas and slow change. Others are active, with bright emission and rapid inflow of material. The differences depend on the supply of gas, the history of mergers, and the presence of structures like bars. In all cases, the central region remains a place where rotation is reshaped rather than stopped. The paths of stars and gas adjust to the deeper gravitational well, but they continue to curve and circulate. The inner parts of a galaxy therefore reveal how rotation adapts under stronger forces. As matter moves closer to the center, its motion becomes faster and more complex. Angular momentum is redistributed through interactions, yet it is not simply lost. The system evolves, forming new structures and patterns, but the underlying principle remains steady. Motion persists because the conditions of space offer little resistance, and because gravity organizes that motion into orbits rather than extinguishing it. In this deeper region, the question of why spinning does not stop finds a clearer answer. there is no mechanism that quietly drains motion away. Instead, there are many pathways that transform motion, shifting it between stars, gas, and central mass. The galaxy's core is not a place of stillness. It is a place where movement becomes more concentrated, more layered, and more tightly bound, continuing the quiet turning that began on larger scales and carrying it inward toward even denser realms. Beyond the crowded center of a galaxy, but still within its broad disk, there are regions where new stars begin their existence. These regions are often called star nurseries. They're vast clouds of gas and dust, spread across distances of many light years, and they appear as dim, diffuse structures when viewed from afar. Their material is mostly hydrogen, the simplest and most abundant element, along with smaller amounts of helium and heavier elements formed in earlier generations of stars. Though they may seem quiet and still, these clouds carry motion within them, and that motion plays a key role in how stars form. A star nursery begins as a part of the interstellar medium, the thin mixture of gas and dust that fills the space between stars in a galaxy. In some regions, this material becomes denser than average. The causes of this increased density vary. A passing spiral arm can compress gas. Shock waves from distant stellar explosions can push material together. Gravitational attraction can slowly draw matter into a shared region. As density rises, gravity begins to act more strongly within the cloud, encouraging further gathering of material. These clouds are not uniform. They contain clumps, filaments, and knots where matter is slightly more concentrated. Within these irregular structures, gravity pulls inward. At the same time, the cloud may have a slight overall rotation, inherited from the larger galactic motion and from local flows of gas. This rotation is usually very slow at first. The cloud may span tens or hundreds of light years, so even a small angular momentum is spread over a large distance. Yet as parts of the cloud begin to collapse, this small rotation becomes more significant. Angular momentum again becomes central to the process. As a portion of the cloud contracts under gravity, its size decreases. Because angular momentum tends to be conserved, the rotation rate increases as the material moves inward. This is similar to how a rotating system spins faster when its mass is drawn closer to the center. In the cloud, this effect is not perfectly uniform, because different regions collapse at different rates and along different paths. Still, the general trend remains. Contraction leads to faster rotation in the collapsing parts. The collapsing cloud does not fall straight inward in a simple sphere. The presence of rotation causes it to flatten. Material moving toward the center encounters its own sideways motion, which prevents it from collapsing directly along all directions. Instead, the cloud begins to form a denser core surrounded by a rotating, flattened structure. This structure is the early stage of a disk that will later become more defined around a forming star. Within the cloud, temperature and pressure also play important roles. As gas is compressed, it warms. If it can radiate heat away effectively, it continues to collapse. If it cannot, pressure may resist further contraction. Dust grains help the cloud cool by emitting radiation. This cooling allows the collapse to proceed in many regions, leading to the formation of multiple dense cores rather than a single object. Each core can become a new star, and the cloud may give birth to many stars over time. The motion within the cloud is not smooth. Turbulence, or irregular motion, is present at many scales. Turbulence can support the cloud against collapse in some regions while promoting it in others by creating dense pockets. The interplay between turbulence, gravity, and rotation shapes the pattern of star formation. Despite this complexity, the influence of angular momentum persists. Even in a turbulent environment, collapsing regions retain some net rotation, which guides how material settles. Magnetic fields thread through the interstellar medium and the star-forming clouds. These fields are weak but widespread. They can influence the motion of charged particles in the gas and help transfer angular momentum from one part of the cloud to another. This process can slow rotation in certain regions and allow more material to fall inward. The exact details of how magnetic fields affect star formation remain an area of active study. Observations indicate that they play a role, but it remains uncertain how dominant that role is compared with turbulence and gravity. As collapse continues, the densest regions within the cloud become opaque to their own radiation. Light cannot escape easily, and the core heats further. A protostar begins to form at the center of a collapsing region. Around it, the rotating material continues to gather into a disk. The disk forms because material with angular momentum cannot fall directly into the center without losing that motion. Instead, it orbits the forming star, creating a stable, rotating structure. The larger cloud may continue to feed material into these forming systems. Filaments within the cloud can channel gas toward the dense cores, adding mass and angular momentum. The direction and amount of this inflow affect the rotation of the resulting disk. Each forming star system therefore carries a record of its environment, shaped by the flows and imbalances present in the cloud from which it emerges. Even as stars begin to form, the surrounding cloud is altered by their presence. Young stars can emit radiation, and winds that push against nearby gas. These effects can clear away parts of the cloud, slow further collapse in some areas, and trigger it in others. The balance between formation and disruption determines how long a star nursery remains active. Over time, much of the gas may be dispersed, leaving behind clusters of newly formed stars that continue to orbit within the galaxy. In this region, rotation is no longer a faint distributed tendency. It becomes a clear and necessary part of the formation process. Without angular momentum, collapsing gas could fall more directly into a central point. With it, the gas spreads into disks, forms structured systems, and sets the stage for the creation of planets. The star nursery therefore acts as a bridge between large-scale galactic motion and the more focused rotation of individual star systems. The persistence of spinning motion here is not the result of a force that keeps pushing matter to turn. It arises from the initial conditions of the cloud and from the conservation of angular momentum as the cloud collapses. Gravity gathers matter inward, while rotation shapes how that matter settles. The result is a transformation from a diffuse, slowly moving cloud into compact, rapidly rotating systems. The turning that began as a slight drift in a vast region becomes more defined and more intense as the scale becomes smaller. Inside the dense parts of a star nursery, a newborn star begins as a protostar, a central gathering of gas that is not yet fully stable. It grows because surrounding material continues to fall inward. The protostar is hidden at first within a thick envelope of dust and gas, and much of its early light is absorbed and re-emitted at longer wavelengths. Although it is not yet shining through steady nuclear fusion in its core, it already contains heat, pressure, and motion. It is a forming object, still receiving mass, still adjusting its shape, and still carrying the rotation inherited from the collapsing cloud. As material falls toward the protostar, gravity pulls it inward while angular momentum keeps much of it from dropping directly onto the center. The gas, therefore, gathers into a rotating disk around the young star. The protostar and disk are connected. Matter moves through the disk and gradually reaches the star, while the star gains mass and spin from the material that lands on it. This process is not perfectly smooth. Gas arrives in streams, knots, and bursts, and the young star responds as its outer layers absorb the incoming matter. The spin of a newborn star is shaped by several competing effects. Collapse tends to make rotation faster, because matter moves inward while keeping much of its angular momentum. If nothing slowed the process, many young stars would rotate so fast that their outer layers could become unstable. Observations show that newborn stars do rotate, but not as rapidly as simple collapse alone might suggest. This means that some angular momentum must be transferred away from the star as it forms. Magnetic fields provide one important pathway for this transfer. A young star often has strong magnetic activity, and its magnetic field can connect with the inner region of the surrounding disk. The field lines act as a link between the star and the disk, guiding charged gas and influencing its motion. If the disk rotates at a different rate than the star, the magnetic connection can exchange angular momentum between them. This interaction may slow the star's spin while allowing material to continue falling inward. The details are complex, and observations indicate that magnetic braking is important, though its strength can vary from one young star to another. A newborn star can also release narrow outflows and jets from its polar regions. These jets are streams of material moving away from the forming system at high speed. They are linked to the disk and magnetic fields, and they help remove angular momentum from the inner regions. The jets do not carry away most of the mass, but they can carry away enough motion to affect how the star grows. Their presence shows that star formation is not only inward collapse, it also includes outward channels that help the system regulate itself. The protostar's interior changes as mass accumulates. Its center becomes hotter and denser under the weight of overlying gas. Pressure pushes outward, gravity pulls inward, and the young object seeks balance. Before steady hydrogen fusion begins, the protostar shines mainly because gravitational energy is converted into heat as it contracts. This stage can last different lengths of time depending on the star's mass. More massive stars evolve quickly, while lower mass stars take longer to settle. Rotation affects the shape of the young star. A rotating object tends to become slightly flattened, with its equator wider than its poles. For most newborn stars, this flattening is modest, but it reflects the same rule seen on larger scales. Matter moving around an axis resists perfect spherical collapse. The star's rotation also influences its magnetic activity, surface flows, and the way material from the disk reaches its outer layers. In some systems, accretion occurs along magnetic funnels, with gas guided toward regions near the magnetic poles. The young star does not rotate as a single unchanging shell. Its interior can rotate at different rates in different layers. The outer regions may interact strongly with the disk and magnetic field, while deeper regions respond to pressure, convection, and contraction. Convection is the movement of hot material rising and cooler material sinking, transporting heat through the star. In many young stars, convection is widespread and helps mix material. It also interacts with rotation to sustain magnetic activity. As the protostar grows, the surrounding envelope becomes thinner. Radiation, winds, and outflows clear nearby gas. The disk remains as a rotating reservoir, feeding the star more slowly. During this time, the star's spin continues to evolve. It may gain angular momentum from accreting gas, lose angular momentum through magnetic winds, and exchange motion with the disk. The final rotation rate of a young star is therefore a result of balance, not of a single cause. Different stars emerge with different spin rates. Their masses, magnetic fields, disk lifetimes, and environments all matter. A young star in a dense cluster may experience nearby radiation or gravitational encounters that affect its disk. A star forming in a quieter region may keep its disk for longer. These differences shape how much angular momentum is retained. Observations of young stellar groups show a range of rotation periods, supporting the view that each star carries both a common physical process and an individual history. The newborn star therefore shows rotation becoming concentrated into a single luminous body. The motion that once belonged to a vast cloud has been compressed into a smaller form, but it has not disappeared. Some of it remains in the star's spin, some remains in the disk, some is carried away by jets and winds. The system rearranges angular momentum so that the star can form without tearing itself apart from excessive rotation. This stage gives a calm and precise example of why spinning motion persists. Gravity pulls matter inward, and inward motion increases the importance of any sideways movement. Magnetic fields, disks, and outflows can reduce or redirect the spin, but they do not erase motion from the universe. They move it from one place to another. In the newborn star, rotation is no longer only a broad pattern of gas and dust. It becomes part of the star's structure, part of its formation, and part of the quiet balance that allows it to shine. Around a young star, the remaining gas and dust settle into a broad rotating disk. This disk is called a protoplanetary disk, meaning a disk that can form planets. It is not a flat solid surface. It is a thin, moving mixture of gas, dust grains, ice, and small rocky particles, all orbiting the central star. The disk exists because material from the original cloud keeps angular momentum as it falls inward. Instead of dropping directly into the star, much of the matter spreads into circular and oval paths, forming a quiet ringed environment where larger bodies may gradually grow. The disk is wide compared with the star, but thin compared with its own diameter. Close to the star, the material is warmer, and only minerals and metals can remain solid. Farther out, temperatures fall, and volatile substances such as water, carbon dioxide, and methane can freeze into ice on dust grains. The word volatile means a substance that can easily become gas when warmed. In the colder parts of the disk, these materials become solid and add mass to the grains. This temperature pattern helps determine what kinds of worlds can form at different distances. Rotation organizes the disk. Each part orbits the star according to gravity. Material closer to the star moves faster, while material farther out moves more slowly. This difference is called differential rotation, meaning that the disk does not turn as one rigid object. The inner regions complete an orbit sooner than the outer regions. This shearing motion stretches structures, spreads material, and influences how dust grains meet one another. It also helps shape waves, gaps, and rings within the disk. Gas in the disk feels pressure, friction, magnetic effects, and radiation from the young star. Dust grains feel gravity and drag from the gas around them. A dust grain does not simply follow a perfect orbit by itself. It moves through gas that can be slightly slower than the ideal orbital speed, because gas pressure supports part of the disk against gravity. This difference causes dust to feel a headwind, gradually losing orbital energy and drifting inward. The process is slow for some particles and faster for others, depending on size and location. Small grains can collide and stick. At first, this sticking may happen through weak surface forces. Dust becomes clumps, clumps become pebbles, and pebbles may gather into larger bodies. The growth is not simple. Collisions can also bounce, break, or grind particles down. The path from dust to planets requires some regions to concentrate solids strongly enough that gravity can take over. One possible pathway is the streaming instability, a process in which dust and gas interact so that particles gather into dense filaments. When these concentrations become heavy enough, gravity can collapse them into kilometre-sized planetesimals. A planetesimal is a small solid body that can serve as a building block for planets. The disk's rotation is essential to this process because it holds material in long-lasting orbits. Without rotation, matter would fall toward the star quickly. With rotation, particles remain in the disk long enough to collide, drift, gather, and grow. Gravity does not stop their sideways motion. It bends that motion into orbit. This balance creates time, and time allows small materials to become larger structures. Gas also moves through the disk toward the star. This inward flow is called accretion. For gas to move inward, it must lose some angular momentum. The angular momentum does not vanish. It can be transported outward through turbulence, magnetic fields, or waves in the disk. Some gas moves closer to the star while other material receives angular momentum and shifts outward. This exchange allows the disk to evolve while preserving the broader rule that motion is transferred rather than destroyed. The young star affects the disk through light, heat, winds, and magnetic activity. Radiation warms the surface layers and can drive away lighter gas over time. Stellar winds can push on the disk, especially in its outer regions. High-energy light can break molecules apart or ionize gas, meaning it removes electrons and leaves charged particles. Charged gas interacts with magnetic fields, which can influence accretion and help launch outflows. These effects slowly disperse the disk, setting a limit on how long planet formation can continue. Within the rotating disk, gaps and rings may appear. Some are caused by growing planets that clear material along their orbits. Others may arise from changes in pressure, dust growth, or chemical transitions where certain substances freeze or evaporate. Observations by modern telescopes show that many young disks have detailed ring structures. These patterns indicate that disk evolution can begin early and that planet formation may occur while the disk is still rich in gas and dust. It remains uncertain how every observed ring forms, because several processes can produce similar shapes. As larger bodies grow, they continue to orbit within the disk. Their gravity can attract nearby solids and gas. A rocky body grows through collisions with other solid bodies. A massive core in a gas-rich region may collect a thick atmosphere if it becomes large enough before the gas disperses. The final result depends on timing, location, temperature, and the amount of material available. Rotation remains the framework that keeps these growing bodies in organized paths around the star. The disk itself slowly thins. Dust is incorporated into larger bodies or blown away. Gas accretes onto the star, escapes into space, or becomes part of planets. The once dense and opaque environment becomes more transparent. What remains may be a system of planets, smaller rocky bodies, icy objects, and leftover dust. Their orbits preserve the memory of the disk's rotation, even after the disk is gone. A protoplanetary disk therefore shows rotation as a condition for building worlds. The disk is not merely spinning for appearance. Its motion prevents immediate collapse, spreads matter into ordered paths, and creates a long-lived arena for growth. Angular momentum keeps material circling. While collisions and gravity arrange it into larger forms, some motion is shifted outward, some inward, and some into the spins and orbits of the young planets. The turning continues because there is no surrounding medium dense enough to halt it, and because every exchange of the motion passes angular momentum from one part of the system to another. Around the young star, the disk becomes a quiet workshop of orbiting matter, where the inherited spin of a cloud is transformed into the architecture of a planetary system. Within the cleared space around a mature star, planets follow curved paths that preserve the motion of the disk from which they formed. The gas and dust have mostly dispersed, but the architecture remains. Planets circle the star because gravity pulls inward while their sideways motion carries them forward. They do not need a continual push to keep moving. In the near empty space between them, there is very little resistance. So their motion can continue for billions of years unless another body changes it. A planetary orbit is a balance between falling and moving sideways. The star's gravity draws the planet toward the center of the system. At the same time, the planet has inherited forward motion from the rotating disk. Because of this sideways motion, the planet misses the star as it falls, tracing a path around it. The path is usually an ellipse, which is a stretched circle, though many planetary orbits are close to circular. The shape depends on the planet's formation history and on later gravitational interactions. The planets in many systems tend to orbit in roughly the same plane because they form from a flattened disk. This plane is not perfectly thin or exact. Some planets may have tilted orbits, especially if their system has experienced strong interactions, migration, or close encounters. Still, the shared plane records the rotation of the original disk. The planets are not arranged at random. Their paths carry the imprint of the material that once circled the young star. Orbital motion also carries angular momentum. A planet's angular momentum depends on its mass, its distance from the star, and its speed along its path. Larger planets and more distant planets can hold a great share of a system's angular momentum. This matters because angular momentum is conserved unless outside influences act. Within a planetary system, planets can exchange angular momentum through gravity. Their orbits may shift, stretch, or tilt, but the total motion remains organized by the same rule. Planetary systems are not fixed from the moment they form. Young planets can migrate through their disks while gas is still present. Migration means a gradual change in orbital distance. A planet can exchange angular momentum with waves it raises in the surrounding disk. Depending on conditions, it may move inward or outward. This process helps explain why some large planets are found close to their stars, where they likely did not form in place. The planet's motion changes, but the angular momentum is carried into the disk or into other parts of the system. After the gas disk fades, planets continue to interact gravitationally. A large planet can disturb smaller bodies, scatter them inward or outward, and reshape belts of debris. Two planets may enter resonances, where their orbital periods form a simple relationship. A resonance can stabilize motion in some cases or increase orbital stretching in others. These relationships show that planets are not isolated beads on separate tracks. They are members of a connected gravitational system, each one subtly influencing the others. The spacing of planets reflects both growth and survival. Bodies that form too close together may collide or scatter one another until the remaining planets occupy more stable paths. Collisions can merge growing worlds, while scattering can send bodies into distant orbits or out of the system. The planets that remain are those whose motions can persist under the combined pull of the star and neighboring bodies. Their orbits are not perfectly unchanging, but they are stable enough to endure over long intervals. The near vacuum between planets is important for the persistence of motion. On Earth, moving objects slow because they rub against air, water, or solid surfaces. In space, such resistance is extremely weak. A planet does not plough through a dense medium as it travels. It moves through sparse particles and radiation, which exert only tiny effects on a large world. Therefore, the planet keeps the motion it has unless gravity from other bodies redirects it. This is why an orbit can last without fuel. The star's gravity does not drain the planet's motion away. Instead, it constantly changes the direction of the planet's velocity, bending the path into an orbit. The planet's speed may vary along an elliptical path, increasing when closer to the star and decreasing when farther away. But the overall orbit continues. Energy shifts between motion and gravitational position, yet the system remains bound. This exchange is a quiet rhythm rather than a loss of motion. Tides can alter orbits over long times. A tide is a gravitational stretching caused by one body pulling more strongly on the near side of another than on the far side. Tides raise distortions in planets and stars, if these distortions are not perfectly aligned with the line between the bodies. They can transfer angular momentum between spin and orbit. A close planet may slowly move inward or outward, depending on the rotation of the star and the details of the tide. These changes are usually slow, but in close systems they can become important. Smaller bodies also preserve the history of orbital motion. Asteroids, comets, and icy objects occupy paths shaped by the early disk and by the gravity of planets. Some remain in belts. Others travel on stretched paths that carry them close to the star and then far outward. Their orbits can be disturbed more easily because their masses are small, but they still obey the same balance of gravity and sideways motion. They show the leftover structure of the planetary system after the main planets have formed. The direction of planetary orbits often matches the direction of the star's rotation because both come from the same disk. This alignment is common, though not universal. Some systems show tilted or even reversed orbits, likely caused by interactions with other planets, companion stars, or the disk itself. These exceptions do not break the principle. They show that angular momentum can be rearranged by gravity, sometimes dramatically, while still remaining part of the system's motion. A planet therefore continues around its star because nothing simple tells it to stop. Its orbit is not maintained by a hidden engine. It is maintained by inertia, the tendency of matter to keep moving, and by gravity, which curves that motion without necessarily removing it. The planet is always being pulled inward and always moving forward. The result is an enduring path, a steady circulation through the quiet space left behind by the vanished disk. In planetary orbits, the universe's turning becomes orderly and familiar. The large motions of clouds and disks have narrowed into distinct paths around a star. Each planet carries a portion of the original angular momentum, and each path records a history of formation, migration, and gravitational adjustment. The planets keep moving because motion in space persists, because gravity binds rather than halts, and because angular momentum is exchanged rather than erased. Around the star, the system turns in measured paths, calm and long-lasting, with each orbit preserving the deep memory of the rotating material from which the worlds arose. A planet does not only travel around its star, it also turns around its own axis, carrying rotation into its body as day and night move across its surface. This planetary spin is separate from the planet's orbit, though both come from the same early history of moving material. During formation, countless smaller bodies collide, merge, and add their motions to the growing planet. Each impact brings mass, energy, and angular momentum. The final spin is the result of many such additions, along with later changes caused by tides, internal motion, and encounters with other bodies. In the early disk around a young star, solid material gathers into planetesimals and then into larger planetary embryos. These growing bodies do not approach one another in perfect straight lines. Their paths are tilted, curved, and uneven. When they collide, the impact is usually off-center. An off-center collision adds spin, much as a glancing push can make an object turn. Over time, repeated impacts build a planet with a particular rotation rate and axis direction. The process is partly orderly because all material belongs to the same rotating disk, yet it is also shaped by chance because individual collisions vary. A planet's spin axis is the imaginary line around which it rotates. The tilt of this axis controls how sunlight falls across the planet over an orbit. A small tilt produces weak seasonal differences, while a large tilt can create stronger changes in light and temperature. The tilt is not fixed by one simple rule. It depends on formation impacts, gravitational pulls from nearby bodies, and long-term interactions between spin and orbit. Some planets rotate nearly upright, while others are strongly tilted. A few rotate in a direction opposite to their orbital motion, showing that later history can greatly alter the original pattern. The speed of rotation also varies widely. A rocky planet may rotate slowly or quickly depending on its collisions and tidal history. A giant planet often rotates rapidly because it forms from a large mass of gas and solids that contracts while preserving angular momentum. As the material moves inward during growth, the spin becomes faster. The result is a planet whose equator may bulge outward. This bulge forms because rotation creates an outward effect strongest at the equator, while gravity pulls inward toward the center. A rotating planet is not perfectly rigid. Its surface, atmosphere, ocean, mantle, and core may move in different ways. On rocky planets, the solid outer shell can shift slowly through geological processes. Beneath it, hotter material may flow over long times. In giant planets, there may be no solid surface at all in the familiar sense. Layers of gas and fluid can rotate at different speeds, depending on depth and latitude. The observed rotation of such planets may be measured from magnetic fields, cloud motions, or radio signals, each revealing a different layer of motion. Internal structure affects spin over time. As material inside a planet shifts, the distribution of mass changes. A planet with more mass concentrated toward its center rotates differently from one with more mass spread outward. If internal layers move, freeze, melt, or separate, the rotation can adjust slightly. These changes are usually small compared with the original spin, but they show that a planet is not merely a hard ball turning unchanged. It is an evolving body whose rotation responds to its own interior. Tides are among the strongest long-term influences on planetary spin. A nearby star or moon pulls more strongly on the near side of a planet than on the far side, stretching the planet slightly. If the planet rotates faster than the orbiting companion moves across the sky, the tidal bulge is carried ahead. Gravity then acts on the bulge and transfers angular momentum between spin and orbit. This process can slow a planet's rotation. Over long periods, it may lead to tidal locking, where the same side of one body always faces another. Tidal effects are strongest when bodies are close, large, and deformable. A planet close to its star can have its spin slowed until one hemisphere faces the star continually. A moon close to its planet can become locked in the same way. The motion has not disappeared. It has moved between rotation and orbit, and some energy has been changed into heat through internal friction. Tidal heating can warm interiors, drive geological activity, or reshape surfaces. The spin slows. But the angular momentum remains accounted for within the wider system. A planet's atmosphere can also influence rotation. Winds move mass around the planet and exchange angular momentum with the surface. On a world with a thick atmosphere, sunlight can heat air unevenly, creating thermal tides that push on the rotation. These effects may be small for some planets and important for others. They can help maintain or modify a spin state, especially when gravitational tides are also present. The atmosphere becomes part of the rotating system, not a layer separate from it. Impacts after formation can change spin as well. A large collision may tilt the axis, speed up rotation, slow it, or even reverse it. Such events are more common in the early history of planetary systems, when many bodies remain on crossing paths. Later, after the system settles, large impacts become rarer, though smaller impacts continue. Each one carries a tiny amount of angular momentum. Most are too small to change a planet's spin noticeably, but the principle remains the same. Motion arrives with matter. Planetary spin matters because it shapes the environment of the world. Rotation influences winds, ocean currents, magnetic field generation, and the rhythm of light and darkness. A faster spin can strengthen broad atmospheric circulation patterns. A slower spin can allow stronger day-night temperature contrasts. In a fluid interior, rotation helps organize moving conductive material, which may support a magnetic field. The spin is therefore not only a leftover from formation, it becomes part of the planet's active behavior. Still, the central reason planets keep rotating is simple. In space, there is no thick surrounding medium to rub against them and stop them quickly. Friction inside the planet and tides from outside can change spin, but these processes act over long times and transfer motion rather than erase it. A planet turns because it formed from moving material and because angular momentum persists. Its rotation may slow, tilt, wobble, or settle into a new relationship with its orbit. Yet it does not fade away merely because time passes. In planetary spin, the movement of the universe reaches the scale of a single world. The broad rotation of a disk becomes the turning of a body, the length of a day, the shape of an equatorial bulge, and the hidden motion of an interior. The planet's spin records collisions, tides, and internal change. It continues because matter keeps the motion it receives, and because every influence that alters the spin sends angular momentum somewhere else. The world turns quietly within its orbit, carrying ancient motion through its surface, atmosphere, and deep interior. Around many planets, smaller bodies continue the pattern of motion on a reduced scale. Moons travel along curved paths, and rings of particles trace delicate bands that circle their parent worlds. These systems show rotation not as a single solid turn, but as a collection of orbits shaped by gravity and by the exchange of angular momentum. Each moon and each particle follows its own path, yet all remain bound to the planet, forming a quiet system of smaller circles within the larger motion around the star. A moon forms in several possible ways. It may grow from material that once surrounded the planet in a disk, much like the disk around a young star. It may be captured from a passing object if conditions allow. It may also result from a large impact that ejects material into orbit, where it gathers into one or more moons. In each case, the resulting body carries angular momentum. Its orbit reflects the conditions under which it formed, including the direction and speed of surrounding material. Once a moon is in orbit, its motion follows the same balance seen elsewhere. Gravity pulls it toward the planet, while its sideways motion carries it along a curved path. The orbit can be circular or elliptical, and it may lie close to the planet's equatorial plane or be tilted at an angle. Over time, gravitational interactions tend to shape these paths. Moons that form from a disk often settle into a shared plane and direction, preserving the rotation of that disk. Tides strongly influence moons and their planets. A moon raises a tidal bulge on its planet, and the planet raises a tidal bulge on the moon. If the rotation of the planet is faster than the orbital motion of the moon, the bulge on the planet is carried ahead of the line between the two bodies. This misalignment transfers angular momentum from the planet's spin to the moon's orbit. As a result, the moon may slowly move outward, increasing its orbital distance over long periods. At the same time, the moon's own rotation can be altered. Tidal forces act within the moon, creating internal friction that converts some of its rotational energy into heat. Over time, this process can slow the moon's spin until it becomes tidally locked. Tidal locking means the moon rotates once for each orbit, keeping the same face toward the planet. This state is common among large moons in close orbits. The motion has not stopped. It has been reshaped so that rotation and orbit match in a stable relationship. Ring systems provide another example of orbital motion. Rings are made of countless small particles, ranging from dust grains to larger icy fragments. Each particle orbits the planet independently, yet the overall structure appears as a smooth band. The rings are thin compared with their width, and they often lie close to the planet's equatorial plane. This alignment reflects the influence of the planet's rotation and gravity, which guide particles into stable paths. The motion within rings is complex. Particles closer to the planet orbit faster than those farther away. This differential motion causes the ring to spread over time, as faster particles overtake slower ones. Collisions between particles are frequent, but they are usually gentle because the particles share similar speeds. These collisions can damp large differences in motion and keep the ring relatively thin. At the same time, gravitational effects from nearby moons can create gaps, waves, and sharp edges within the rings. Small moons embedded in or near rings can shape their structure. A moon may clear a path along its orbit, forming a gap. It may also create spiral density waves, patterns that move through the ring as regions of higher and lower particle concentration. These waves arise from gravitational interactions that transfer angular momentum between the moon and the ring particles. The exchange does not destroy motion, it redistributes it, shifting particles inward or outward while maintaining the overall rotation of the system. Some rings are transient on long timescales. They may form from the breakup of a moon that came too close to the planet and was pulled apart by tidal forces. They may also be replenished by material from small impacts on moons. Over time, ring particles can spiral inward and fall onto the planet, or spread outward and disperse. The lifetime of a ring depends on its mass, the presence of shepherding moons, and the balance of forces acting on its particles. It remains uncertain how long specific ring systems can persist, because the processes that shape them are complex and ongoing. Moons can also interact with one another. Gravitational resonances between moons can stabilize or destabilize their orbits. In a resonance, the orbital periods of two moons are related by simple ratios. This relationship can lead to repeated gravitational influences that maintain a pattern. In some cases, resonances can increase orbital eccentricity, making orbits more stretched. This stretching can enhance tidal heating within a moon, keeping its interior active. The motion of one body thus affects the internal state of another, linking orbital dynamics with geological processes. The combined system of a planet, its moons, and its rings shows a layered form of rotation. The planet spins on its axis. The moons orbit the planet. The ring particles orbit in vast numbers, each following a path shaped by gravity and collisions. Tides transfer angular momentum between spin and orbit, slowly altering distances and rotation rates. Resonances distribute motion across multiple bodies. The entire system remains in motion because there is no simple sink that removes angular momentum from all parts at once. In this region, the persistence of spinning becomes visible in relationships. A moon's locked face, a ring's thin plane, and a planet's slowing rotation all reflect exchanges of motion that preserve the total balance. The system evolves, yet it does not come to rest. Each change carries angular momentum from one place to another. The turning continues in smaller circles, nested within larger ones, each level holding a share of the motion inherited from earlier stages. The presence of moons and rings therefore deepens the understanding of why motion endures. Rotation is not a single property of one object. It is a network of motions linked by gravity and by the conservation of angular momentum. Even when one part slows, another part gains. Even when orbits shift, the overall system remains active. Around a planet, the quiet choreography of moons and rings shows that spinning does not need to be forced. It persists through balance, exchange, and the absence of resistance, carrying the story of motion into ever smaller and more intricate scales. Inside a planet, rotation continues beneath the visible surface. The outer shape may seem steady, with mountains, plains, clouds, or oceans moving slowly compared with the spin of the whole world. But the interior is not still. Beneath the crust of a rocky planet, heat remains from formation, radioactive decay, impacts, and the slow separation of materials by density. This heat allows deep material to move over long periods. The planet turns as one body at the surface, yet its hidden layers may flow, circulate, and rotate in different ways. A rocky planet has a layered structure shaped by gravity and chemistry. The lightest solid materials tend to form the crust, the outer shell. Beneath it lies the mantle, a thick layer of hot rock that behaves as a solid over short times but can flow over long times. At the center lies the core, often rich in iron and nickel. The outer part of the core may be liquid, while the inner part may be solid if pressure is high enough. Each layer responds to heat, pressure, and rotation in its own way. Rotation affects the entire interior because moving material feels the influence of a rotating frame. In a spinning planet, flows are often organized into broad patterns rather than moving freely in any direction. This influence helps shape convection, the slow circulation caused by heat. Hotter material rises because it is less dense, while cooler material sinks because it is denser. In the mantle, convection can move plates, build mountains, open ocean basins, and recycle surface material. The movement is slow, but over millions of years it reshapes the planet. The core is especially important for understanding hidden rotation. In many rocky planets, the liquid outer core contains electrically conducting metal. As this metal moves, it can generate a magnetic field through a process called a dynamo. A dynamo is the generation of a magnetic field by moving conductive fluid. Rotation helps organize the flow into patterns that can sustain the field. Heat escaping from the core drives motion, and the planet's spin gives that motion a preferred structure. Without enough heat flow, enough liquid metal, and enough organized movement, a global magnetic field may weaken or disappear. A magnetic field does not prove that a planet spins rapidly, but rotation is one of the ingredients that can make a dynamo work. The field can shield the upper atmosphere from some charged particles carried by the stellar wind. It can also reveal information about the deep interior, because the field comes from motion far below the surface. Observations of planetary magnetic fields show that interiors are active systems, not frozen centers. The spin seen from outside is connected to flows that cannot be seen directly. The interior of a planet can also change the planet's rotation. If mass shifts from one region to another, the rotation rate may adjust slightly. When ice sheets grow or melt, when mantle material rises or sinks, or when the core exchanges motion with the mantle, the distribution of mass changes. A rotating body tends to preserve angular momentum, so changes in mass distribution can alter the length of a day by small amounts. These changes are usually tiny compared with a full rotation, but they show that the spin of a planet is linked to its internal state. Friction between layers also matters. The mantle, crust, ocean, atmosphere, and core can exchange angular momentum. A planet may not rotate as a perfectly rigid object from surface to center. The liquid core can move at a slightly different rate than the mantle. The atmosphere can speed up or slow down relative to the ground. Oceans can shift mass and motion through tides and currents. These exchanges do not remove angular momentum from the planet as a whole, unless it is transferred to another body. They move it from one layer to another. On giant planets, the interior is different, but the principle is the same. A giant planet may be made mostly of hydrogen and helium, with deeper layers compressed into strange fluid states. There may be no sharp solid surface. Instead, pressure and temperature increase inward, changing the behavior of matter. Rotation can be very rapid, and the planet may become visibly flattened. Bands, storms, and deep flows reflect the influence of spin on fluid motion. The outer atmosphere shows only the upper part of a much deeper rotating system. In such planets, different latitudes can rotate at different rates. Clouds near the equator may move differently from clouds near higher latitudes. Deep layers may have their own rotation, inferred through gravity measurements and magnetic fields. The planet's spin is not a single simple number when its atmosphere and interior are fluid. It is a layered motion, with zones and currents arranged by heat, gravity, and rotation. The flattening of a rotating planet gives another sign of interior motion and structure. A faster spin tends to make the equator bulge outward. The amount of flattening depends on rotation rate and how mass is distributed inside the planet. A planet with more mass concentrated near the center responds differently from one with mass spread more evenly outward. By measuring shape, gravity, and rotation, scientists can infer how matter may be arranged inside. These inferences are careful and limited because interiors cannot usually be observed directly. Planetary interiors also preserve memories of formation. Heavy material sinks toward the center, releasing energy. Lighter material rises. Impact can tilt a planet, melt outer layers, or add heat. As the planet cools, some layers solidify while others remain fluid. Rotation continues through these changes. It may slow through tides, wobble because of mass shifts, or couple more strongly between layers as the interior evolves. The motion remains part of the planet's long development. In this inner region, spinning is not only the visible turn of a globe against space, it is also the movement of deep rock, liquid metal, gas, and fluid layers under pressure. Rotation shapes convection, supports magnetic field generation, influences atmospheric bands, and helps determine the planet's form. The planet keeps turning because its angular momentum remains with it, unless exchanged through tides or impacts. Inside, that same motion is shared among layers, currents, and fields. The world is not simply carried through space by rotation, it is organized by it, from the outer shell down to the deep-moving core. Inside a star, rotation becomes part of a vast and glowing interior where matter exists as plasma. Plasma is gas so hot that many atoms are separated into charged particles. A star appears from outside as a steady sphere of light, but beneath its surface, energy moves through layers of changing density, temperature, and motion. The star turns around its axis, yet its interior does not always rotate like a rigid ball. Different layers can move at different speeds, and these differences shape magnetic fields, surface activity, and the slow evolution of the star. A star forms from a collapsing cloud that already contains angular momentum. As the cloud contracts, the forming star spins, while some motion remains in the surrounding disk or is carried away by winds and jets. Once the star becomes stable enough for hydrogen fusion in its core, it enters a long stage of steady energy production. Hydrogen fusion is the process in which hydrogen nuclei combine to form helium, releasing energy. The star's rotation remains from its formation, but it continues to change through internal flows and outward loss of material. The outer appearance of a star can hide complex motion. A star like the Sun has a surface that rotates at different rates depending on latitude. The equatorial region turns faster than regions closer to the poles. This is called differential rotation. It occurs because the outer layers are fluid rather than solid. Gas and plasma can slide, circulate, and respond to heat and magnetic fields. The star, therefore, does not behave like a single spinning stone. It behaves like a layered, moving sphere of hot matter. Deep inside, the structure depends on the star's mass. In a star similar to the Sun, the central region transports energy mainly by radiation, with light and particles gradually passing energy outward. The outer region transports energy by convection, where hotter plasma rises and cooler plasma sinks. Rotation interacts with this convection. Rising and sinking flows are influenced by the star's spin, and their motion helps sustain magnetic fields. These magnetic fields can reach the surface, where they appear through dark star spots, bright active regions, and eruptions of material. The core of a star rotates under different conditions from the outer layers. It is denser, hotter, and more strongly affected by pressure. Observations of waves moving through stars show that internal rotation can differ from surface rotation. These waves are natural vibrations, and their patterns reveal information about hidden layers. In the Sun, such observations indicate that the radiative interior rotates more uniformly than the outer convective layer. This result shows that some process transfers angular momentum inside the star, smoothing rotation in regions where simple models might predict stronger differences. The movement of angular momentum within a star is still an active area of study. Internal waves, magnetic fields, turbulence, and circulation can all transport motion from one layer to another. In some stars, the core may rotate faster than the surface. In others, the difference may be smaller than expected. Observations indicate that stars often redistribute angular momentum more efficiently than simple theories once suggested. It remains uncertain which processes dominate in every type of star, because the interior cannot be seen directly. Rotation affects how a star ages. A rotating star may mix material between layers more effectively than a non-rotating one. This mixing can bring fresh hydrogen toward regions where fusion occurs and carry fusion products outward. In massive stars, rotation can influence brightness, lifetime, and the material returned to space through winds. a rapidly rotating star can become flattened at the equator, with different surface temperatures between equator and poles. The shape changes because rotation partially reduces the effective pull of gravity near the equator. Stars also lose angular momentum. Stellar winds carry particles away from the surface, and these particles can be guided by magnetic fields. As the wind escapes, it takes some angular momentum with it, gradually slowing the star's rotation. This magnetic braking is important for many lower mass stars. Young stars often rotate faster, while older stars may rotate more slowly. The change is not a simple clock for every star, but it shows that spin can evolve through steady loss of material and magnetic influence. In close binary systems, where two stars orbit one another, rotation can be altered by tides. Each star pulls on the other, raising distortions in its fluid body. Over time, tidal forces can adjust the spin of each star and the shape of the orbit. In some cases, a star's rotation becomes synchronized with its orbit, so that it turns once for each revolution around its companion. As in planets and moons, this does not erase motion. It transfers angular momentum between spin and orbit, and changes energy into heat inside the stars. The surface of a star reveals rotation through features that move in and out of view. Star spots, caused by magnetic activity, can mark the turning surface. Changes in brightness can show how fast the star rotates. Spectra can also reveal rotation, because light from one side of the star shifts slightly as that side moves toward observation, while light from the opposite side shifts as it moves away. These measurements help connect the visible surface to the hidden interior. Rotation is especially important in massive stars. Their strong radiation drives powerful winds, and their rapid spin can shape how material leaves the surface. Some massive stars approach a limit where rotation at the equator nearly balances gravity. In such cases, material may be lost more easily from the equatorial region. The star's future path can be affected by how much mass and angular momentum it loses. The details depend on mass, composition, magnetic fields, and environment. Even in old stars, rotation remains part of the interior story. As a star expands into a giant, its outer layers move outward. If angular momentum were conserved locally, the expanded surface would rotate more slowly. The core, contracting at the same time, could spin faster. Observations show that the contrast between core and envelope rotation is often moderated by internal transport. This means that the star continues to exchange angular momentum within itself as it changes shape and structure. The stellar interior therefore shows rotation as a deep, layered process. It is not only a surface turning under light, it is tied to convection, magnetic fields, internal waves, winds, and aging. The star cannot simply stop spinning because its angular momentum must go somewhere. Some remains in the core, some in the outer layers, some moves outward through winds, and some may be exchanged with a companion. The motion changes form and location, but it is not quietly erased. Within the glowing body of a star, the universe's persistent turning becomes heat, flow, magnetism, and light. The spin inherited from a collapsing cloud becomes a layered motion inside plasma. It shapes how energy rises, how fields are generated, and how the star slowly changes across its life. The star shines because of fusion, but it turns because it formed from moving matter, and because the laws that preserve motion continue to act within every heated layer. When a star reaches the end of its ordinary life, its rotation does not vanish with the fading of its earlier form. The remaining object may become a white dwarf, a neutron star, or, in the most extreme case, a black hole. These compact objects contain matter compressed into much smaller volumes than before. As the size contracts, angular momentum becomes more concentrated. The spin that once belonged to a broad star can become faster and more intense, because the same motion is held within a smaller region. A white dwarf is the dense core left behind by a lower mass star after its outer layers have been shed. It is roughly the size of a planet but contains a mass comparable to that of a star. Its matter is supported by the pressure of electrons, which resist being packed into the same states. The white dwarf no longer produces steady fusion in its core. It glows mainly because it remains hot from its earlier life and cools slowly over time. It may rotate because its parent star rotated, and because the contracting core preserves part of that motion. The rotation of a white dwarf can vary. Some rotate slowly, while others spin more quickly, especially if they have gained matter from a companion star. In a close binary system, gas can flow from one star toward the white dwarf. This falling material often forms a disk before reaching the surface. The disk carries angular momentum, and as matter lands, it can change the white dwarf's spin. Again, the motion is not created from nothing. It arrives with material and is added to the compact object. A neutron star is far denser. It forms when the core of a massive star collapses after nuclear fuel can no longer support it. The collapse is sudden on stellar timescales. The core shrinks from thousands of kilometers across to a sphere only tens of kilometers wide. Because angular momentum is conserved during contraction, the spin can become extremely rapid. A core that once turned slowly can become a neutron star rotating many times each second. The change is the same principle seen in collapsing clouds and forming stars, but taken to a far greater density. The matter inside a neutron star is under extraordinary pressure. Electrons and protons are forced together, forming mostly neutrons, along with other particles in conditions not fully reproduced on Earth. The exact inner structure remains uncertain. Observations indicate that neutron stars are extremely compact and massive, but the behavior of matter at their centers is still studied through theory, laboratory nuclear physics, and astronomical measurement. Their rotation, however, is directly observed in many cases. Some neutron stars appear as pulsars. A pulsar emits beams of radiation from regions linked to its magnetic poles. If these beams sweep across Earth as the star rotates, the signal appears as regular pulses. The timing can be extraordinarily steady. Each pulse marks the rotation of the neutron star, like a distant clock formed by collapsed matter. The beam is not the spin itself, but it reveals the spin with great precision. Some pulsars rotate slowly, while millisecond pulsars rotate hundreds of times each second. A neutron star can slow over time because it loses energy through radiation and particle winds. Its magnetic field acts with the surrounding space, carrying away angular momentum. The spin therefore changes, but not because motion disappears without trace. The lost angular momentum is carried outward by electromagnetic processes and escaping particles. In some systems, a neutron star can later spin up again by accreting matter from a companion. The incoming gas forms a disk and transfers angular momentum to the star, producing the fastest known pulsars. The surface and interior of a neutron star may not rotate in perfect unity. Its crust can be solid, while deeper layers may behave as superfluid matter, a state in which particles move with almost no internal resistance. Sudden changes in rotation, called glitches, are observed in some pulsars. A glitch is a small, abrupt increase in spin rate. It may occur when angular momentum is transferred from the interior to the crust. The exact mechanisms remain under study. but the observations show that even a compact object can hold layered rotation inside. A black hole represents an even deeper form of compactness. It forms when gravity compresses matter so strongly that an event horizon appears. The event horizon is the boundary beyond which light cannot escape. A black hole can have mass, electric charge, and spin. In realistic astrophysical settings, spin is expected because the collapsing material carries angular momentum. A perfectly non-rotating black hole would require matter to collapse with no net rotation, which is unlikely in natural systems. The spin of a black hole affects the space around it. In the theory of general relativity, a rotating black hole drags nearby spacetime in the direction of its spin. This effect is called frame dragging. It is not ordinary spinning material at a surface, because the event horizon is not a solid surface. Instead, spin becomes a property of the geometry around the black hole. Matter orbiting nearby responds to this geometry, and disks around black holes can be shaped by it. Gas falling toward a black hole usually forms an accretion disk if it carries angular momentum. The gas cannot fall straight in until it gives up enough angular momentum. Friction, turbulence, magnetic fields, and waves in the disk move angular momentum outward, allowing some matter to spiral inward. Close to the black hole, the gas can become extremely hot and bright before crossing the horizon. Jets may also form in some systems, carrying energy and angular momentum away along the rotation axis. Black hole spin can increase when the black hole absorbs matter with aligned angular momentum. It can decrease or change direction through mergers with other black holes or through accretion from different directions. When two black holes merge, the final black hole carries the combined mass and angular momentum of the system, with some energy and angular momentum radiated away as gravitational waves. These waves are ripples in space-time, and their detection confirms that compact objects can transfer motion into the fabric of the universe itself. In compact objects, rotation becomes concentrated, measurable, and sometimes extreme. The same rule that shapes a cloud, a disk, a planet, and a star remains present under far stronger gravity. As matter contracts, spin intensifies unless angular momentum is carried away. White dwarfs, neutron stars, and black holes show that the universe does not stop turning when ordinary structures die. It compresses motion into denser forms, moves it through disks, fields, winds, jets, and waves, and preserves the deeper counting of angular momentum even in the most compact regions known. At the smallest known scales, rotation takes on a meaning that no longer resembles a turning object in space. Particles, the basic units of matter and radiation, possess a property called spin. This term is inherited from everyday language, but it does not describe a particle physically spinning like a tiny sphere. Instead, it is a fundamental characteristic, part of how particles behave according to quantum theory. It is built into the description of matter itself, and it influences how particles interact, combine, and form the structures seen at larger scales. In classical motion, rotation involves an extended body turning around an axis. The body has size, shape, and a distribution of mass. Its angular momentum depends on how fast it turns and how its mass is arranged. At the particle level, these familiar ideas no longer apply directly. A particle such as an electron does not have a well-defined surface that can be tracked as it turns, yet it carries angular momentum that can be measured in experiments. This angular momentum behaves in ways that follow strict rules, and these rules are consistent across all observations. Quantum spin is quantized, meaning it can take only certain discrete values. It does not vary smoothly through all possibilities, Instead, each type of particle has a fixed intrinsic spin. Some particles have half-integer spin, such as 1/2, while others have integer spin, such as 1. This distinction divides particles into broad categories that follow different statistical rules. These rules determine how particles can occupy states, how they combine, and how they form matter as known in everyday experience. The effects of spin appear in many physical processes. In atoms, electrons occupy orbitals, regions where they are likely to be found. The arrangement of electrons in these orbitals depends partly on their spin. Two electrons in the same orbital must have opposite spin directions. This rule, known as the Pauli exclusion principle, prevents identical particles with the same spin from occupying the same quantum state. It is essential for the structure of atoms and for the stability of matter. Without it, electrons would collapse into lower energy states, and the familiar structure of elements would not exist. Spin also influences magnetism. A moving electric charge creates a magnetic field, and the intrinsic spin of particles contributes to magnetic effects. In many materials, the spins of electrons can align in certain patterns. When many spins align in the same direction, the material becomes magnetized. When they align in opposite directions in a balanced way, the material may show little or no net magnetism. These patterns depend on interactions at the quantum level, yet they produce visible effects such as magnets attracting or repelling each other. The measurement of spin reveals its quantum nature. When the spin of a particle is measured along a chosen direction, the result is not a continuous range of values. It is one of a small set of allowed outcomes. Repeated measurements on identical systems show a distribution that matches quantum predictions. This behavior cannot be explained by imagining a hidden classical rotation that simply has not been observed. Observations indicate that spin is a fundamental property, not a disguised form of ordinary turning. Spin interacts with motion in subtle ways. In relativistic quantum theory, which combines quantum mechanics with special relativity, spin is linked to the symmetry of space-time. Particles with different spin values transform differently under rotations and other changes of reference. This connection means that spin is not an added feature placed on top of matter. It is part of the deeper structure that defines how matter exists and behaves. The laws that govern spin are tied to the geometry of space and time at a fundamental level. Even at this smaller scale, angular momentum remains a conserved quantity. When particles interact, their spins and orbital motion combine in ways that preserve total angular momentum. For example, when a particle emits or absorbs light, the spin of the photon and the angular momentum of the particle adjust together so that the total remains consistent. These conservation rules are strict and universal within known physics. They show that the principle seen in galaxies and planets extends down to the behavior of individual particles. The concept of spin without visible rotation may seem distant from the turning of a planet or a star, yet it connects to those larger motions through shared laws. Angular momentum is not limited to macroscopic objects. It exists wherever motion and symmetry are present. The forms it takes depend on scale. In large systems, it appears as orbits and rotations. In quantum systems, it appears as intrinsic properties and discrete states. The underlying rule of conservation links these scales. At the smallest level, there is no surrounding medium that can absorb spin in a simple way. Interactions can transfer angular momentum between particles or convert it into other forms, but the total is preserved in each process. This mirrors the larger universe, where motion is exchanged rather than erased. The persistence of spin at the quantum level reinforces the idea that motion is woven into the fabric of physical law, not imposed from outside. Thus, the journey from the outermost observable universe to the smallest particles revealed a continuous theme. At the larger scales, the universe expands without a confirmed global spin. Within that expanding space, structures form, gather, and begin to rotate. Galaxies turn, stars spin, planets rotate, and moons orbit. Inside these bodies, layers move, fields form, and motion is shared. At the smallest scale, particles carry intrinsic spin that does not resemble classical turning, but obeys the same conservation principles. The universe does not need a mechanism to keep spinning in the way a machine needs a motor. Motion persists because of the fundamental laws that govern matter and energy. Angular momentum is conserved, and in the absence of strong resistance, motion continues. Gravity shapes motion into orbits. Magnetic fields and turbulence redistribute it, and interactions carry it from one place to another. From the cosmic web to the spin of a particle, the same quiet rule applies. The universe does not stop spinning because there is no simple way for it to stop. Its motion is not a temporary state. It is a fundamental part of how it exists. Across all scales, motion remains present, but it softens in meaning as the view becomes calm. The universe does not turn as one confirmed whole, yet within it, matter gathers, bends, and circles. Gravity draws structures inward, while sideways motion keeps them from falling directly into stillness. A cloud becomes a disk becomes stars and planets. A planet carries rotation into its days, its tides, its hidden core, and the quiet paths of its moons. Nothing in this story requires a constant push. In the open spaces between worlds, there is little resistance to drain motion away. Angular momentum remains, unless it is passed somewhere else. When one body slows, another may move outward. When gas falls inward, other material may carry motion away. When a star contracts, its spin may quicken. When a particle interacts, angular momentum is still counted in the exchange. The form changes, but the rule remains steady. The spinning universe is therefore not a single wheel, nor a storm without order. It is a layered record of motion preserved through time. Some motions are wide and slow, stretched across galaxies. Some are hidden in the interiors of stars and planets. Some are so small that ordinary images fail, leaving only the careful language of quantum behavior. Each scale keeps part of the same inheritance. In this quiet view, rotation becomes less like restlessness and more like continuity. Matter keeps the motion it receives. Gravity shapes it. Time carries it onward. The universe expands, gathers, shines, cools, and changes, while angular momentum moves from place to place. The turning does not need to be loud, sudden, or dramatic. It remains because the laws of nature allow motion to endure, and because stillness is not the default state of a cosmos born with movement.